So I'm going to talk about some of the recent work I've been doing in collaboration with between university and Facebook. And so work starts from the observation that on the one hand, infants can learn language spontaneously from noisy data without any text in all languages and cultures with little or no supervision, but we don't really know how they do that. I mean, they are sort of theories in psycholinguistics, but they are not really theories in the sense that they make like quantitative predictions about how this process is taking place. On the other hand, we have machine learning algorithms that can reproduce many, but not all, of human language competence. And so they are sort of quantitative models. The question is whether they can also be models of language acquisition and whether we could use it for that. The current problem with these models is they are built with an completely non-realistic type of training data, which is text and expert levels. So the question I'm going to address today is, can we build a system that can achieve the competence of a 1 or 2 year old, but using only the kind of data? Yes. Oh. Okay, so I'm trying to not move too much, but so the question is, can we build a system that can achieve the competence of a 2 year old, but only using the kind of data that that is available to them? Is that okay? You still hear the noise? Well, so to illustrate the problem more concretely, let's take the case of a spoken dialogue system. Such a system takes speech as input, performs a number of steps like speech recognition, word recognition, syntactic parsing, semantic and pragmatic analysis, and then language generation all the way down to speech again. Such a system, in a way, simulates human linguistic competence to the extent that they can sometimes fool humans. Now, can they also simulate how humans acquire language? The first answer to this question is a resounding no. And that's because spoken dialogue systems are typically constructed in a Dr. Frankenstein kind of way. People who sort of build these sort of components one by one and assemble them. And each of the components are built using hours and hours of expert annotation. So for instance, if you take the speech recognition component, it's typically trained to map speech to transcription, which text, using thousands of hours of such data. And so for the other components. So basically here is an estimated amount of annotations and text that is needed to train a system like this. And you can see it's quite large. So it's basically between 2,000 and 10,000 hours of annotated speech to train this component. And here it's billions of words of text, which is much more than anybody will be able to read in his own life. So this is not very realistic. And so here is actually a comparison with how much data is needed to train a baby or an infant or a child of 4 years of age. So this data has been collected across cultures and compared in the series of papers by Alex Christia. And you can see that, I mean, even though there are a lot of differences between different cultures about the amount of hours of speech that is directed to children during the 4 years of life, this is way less than is typically used for by speech recognition systems. And also the data is very different because here you also need lots and lots of text, and infants don't have text to learn speech. Okay, so basically the question then becomes, can we build a system, a spoken dialogue system that would need no annotation and no text, just sensory data and interactions with adults in the amount available to infants? So because this is a very complicated challenge, what we did was to set up a benchmark and share tasks for the machine learning community to help us solve this difficult problem. And what we did was to break it down into a number of simpler but increasingly more difficult objectives, like the discovery of subword units, the discovery of words, the ability to speak, to resynthesize the speech, and the ability to learn higher order language concepts. So today I'm going to focus on the first and the last of these tasks. So the first one is acoustic unique discovery. Now, if you look at the history of speech recognition, a number of speech scientists have dreamed one day or another to automatically discover the units of speech. Many ideas have been proposed, ranging from auditory neuroscience to neural networks and probabilistic models, but very little cumulative science had been achieved for lack of a common evaluation benchmark. So what we did was to propose to use tasks from psychophysics and infant speech perception to compare all of these different models. And so the idea is very simple. A good speech representation should be such that two tokens of the same linguistic categories, for instance, bit and bit, are closer together than tokens of different categories like bit and bet, even across a change in speaker. So basically, to give you an idea of an ABX score of 30%, that would be something like this between two categories, the red and the blue, and an ABX score of 5% would be something like this. Now, given that we now have this evaluation technique, we started the challenge and had many submissions. So I'm not going to summarize for you all of the proposals. There are too many of them. But what's interesting is that they all sort of shared a very small number of basic ideas, the most common of which is the idea of information compression. Now, if you take a spectrogram, a representation of speech sound, and you try to put that into a file, you are going basically to need something like 20 kilobits per second of speech to represent the spectrogram. You can reduce that somewhat by going through a telephone and losing a little bit of quality. But on the other side of the thing, if you take now text or a phoneme transcription of the same speech, you have basically a 200-fold reduction in the size of the file. So what that means is that phonemes are extremely compact representations of speech sounds. And so the idea of most of the models that have been proposed is to achieve such reduction by various means like clustering, soft clustering, or bottleneck representations. So in this graph here, what we have is a leaderboard of some of the most successful models that have been achieved through the years. Here you have the ABX score in a couple of languages. This is English, Tsonga, German, and Wolof. We try to diversify the number of languages. And then basically the most successful models is this one. It's a soft clustering model based on a mixture of Gaussian. And it really is focused on the idea of compression. Really, if you express a very complicated signal in terms just of a mixture of Gaussian, you only have basically the code of the Gaussians, and that's your code. To achieve good performance, what these models did was to add a component of normalization where you remove information that's non-linguistic, like for instance, the identity of the speaker. You try to remove that from the representation before compressing it, and that gives quite good ABX scores around 16 to 10. Now, an interesting question is now, what have these systems learned, okay, in terms now of psycholinguistics? So in this paper, what we did was to take the best model in the previous leaderboard and submit it to tests that have been run in infants. In particular, we asked whether this model can reproduce the well-known perceptual attunement phenomenon. So this is the phenomenon by which Japanese learners can have difficulties in perceiving certain phonemes of English, like for instance, the R versus L. Okay, so a system trained in Japanese, if it reproduces the phenomenon, should have a high error rate when trying to discriminate R from L compared to a system trained in English. And that's exactly what we find here. So we took the best models from the previous leaderboard, trained it with an English data set or a Japanese data set, and then we tested on the RL contrast. And you can see the error rate is much larger for a Japanese trained model than an English trained model. To a certain extent, this phenomenon is also reproduced with other consonants, but the phenomenon is much less, as has been documented in the literature. So basically, this model can now reproduce the sort of attunement to the phonemes of the native language. But the question is, what has it learned? And what we tried to do was to probe the system. And what we found that what the system has done has nothing to do with phonemes. If we try to look at these units, what we find is that the number of units that the system has done, basically the number of Gaussian components in the mixture, is way larger, is about 10 times larger than the number of phonemes. Okay, so why does it need that many? The other thing is that if you look at the duration of activation of these units, they are much shorter than the phonemes, about 3 times shorter, 3 or 4 times shorter. So what they do is they encode like tiny little acoustic events. They're not encoding phonemes. The final thing that we looked at in this paper was the variability. So what we did was to take the same word spoken by the same speaker in different instances, and we looked at the transcription of that word, not even the word, just the phonemes in the middle of the word, excluding the boundaries. And we found that these transcriptions were different each time. So that means that the system is really picking up on fine acoustic information that no linguist would like to describe in its representation. So basically what we found there is that these systems can learn linguistic information in the sense that they are tuned to the phonemes of the language, but they are not really learning phonemes. So that's sort of intriguing. So since then, there has been an emergence of new machine learning systems that are based on a different idea, not compression, but prediction. So here, this is the contrastive predictive coding model proposed by Van den Oord in DeepMind. And what the system does is it starts with the raw audio and learns a latent representation Z that is such that it's able to predict the future states of the Z. So based on the past, it can predict the future. And this representation is completely learned autonomously without any label. And now when it's learned, we can use this representation or some other state of the system as a representation for speech. So what we did in this collaboration with Facebook was to analyze these new models using the ABX score. And what we found is that even though systems like, predictive systems need more data than the compression systems I described before, when you give them enough data, they actually learn, and they learn much better than the other one. In fact, we now have basically divided by 3 the error rate in ABX compared to the previous state of the art with more data, with like 1,000 hours of data, which still is within the range of a 4-year-old. Just to give you an idea of the basically 4% or 6% of ABX is basically what it means is that the phonetic categories are now like really distinct. You can see them with your own eyes, but still they are not phonemes. Okay, so these are like new other ideas that have been also found in the literature about these predictive models. So I'm not going to explain them. So now let's move, because we have a leap in performance, we are also going to take a leap in linguistic level and try to address directly the higher levels. So now that we have some good acoustic units or speech units, can we use them to directly learn higher order linguistic concepts? So let's build such a system step by step, okay? So acoustic modeling. So we have this, let's take our one of the predictive coding model that learns a representation. Then we do quantization to learn some discrete categories. And for this, we take like a simple clustering k-means algorithm. Next, now that we have discrete units, we are in a realm of NLP, natural language processing. So let's use one of the standard unsupervised language modeling algorithms like BERT. So in BERT, what you do is you take a series of symbols, like typically it's text, okay? But now it's like these discrete pseudo phonemes. And you mask some of them, and you ask the system to reconstruct the missing symbols. And so these systems have been extremely successful to learn a number of things at the linguistic level. So our training set is about 1,000 hours of speech from audiobook recordings. Of course, we don't use text, just the audio. And now we have a system, and we can ask, okay, what has it learned? Again, I mean, has it learned anything useful, anything like representative or similar to what infants would learn in these situations? So what we did was to run two kinds of tests. One are subjective and one are objective or based on psycholinguistics. So let me give you an idea of what I mean by subjective test. So in subjective test, by this, I mean, you take this system, you extract the quantized representations, and then you plug this to a synthesizer, which you trained on the same data. So basically now you have a system that's able to reconstruct speech. So I give you an example. You can play it a sentence like this.
Within minutes, Tom was in charge of clearing away rubble and extricating anyone who might be trapped inside the buildings.
And now you can reconstruct it with the system will reconstruct it with its own voice.
Within minutes, Tom was in charge of clearing away rubble and extricating anyone who might be trapped inside the buildings.
Okay, so the quality is quite good, which means that the quantization here, even though they are not phonemes, they are sort of carry enough information to enable reconstruction. So once you do that, use this as a probe to know what the language model has learned. But what you do is you can sample using, just random sample utterances from this language model, transcribe it into the quantized units, and then synthesize it. So this is, for instance, what you can get.
The battle was no longer days. The battle were days, and the day was on the ground. No wonder that it was in the life of a demon and of a patient and feeling. The battle was made.
Okay, so it continues on and on. So what's striking with this sample here is that you can recognize that it's English. The phonemes are in English. I mean, it looks like that, and also recognize some words. And even more than that, we can recognize some sort of sentence fragment. The output doesn't mean anything. It's a little bit rambling, but it's like looks like the system has learned some language. Okay. So you can see, like, provide an audio prompt, then code it, then the language model is going to complete that. So just to give you an example of how it works, you start with a sample probe like this.
And says, "Thou mother
and then the
of my
system
children."
will encode this and then complete the sentence in its own way.
And says, "Thou mother of my child, and I was mine, and I was mine, and I was mine."
So in this example, it's just like continues doing exactly, repeating itself. And this one.
And says, "Thou mother of my children, and my children, and my children, and forever."
Okay.
And thou mother of my.
All right. So basically, as is usual in NLP systems, there's this question of temperature. So when you sample from the language model, if you change the temperature, it will go from a completely obsessive zone where it's repeating itself, and when you lower the temperature, you get like more diverse but also less meaningful utterances. So I'm not going to give you examples on that. I'm going to jump into the psycholinguistics test because we don't have a lot of time. And so what you can do with computational models of this kind is to extract quantities that allows you to probe the system in a way that's similar to how you test babies. So basically, there are two kinds of things you can extract from models. You can extract probabilities. I give you a sentence, and you give me the probability, which is basically what the language model is computing. Or you can extract representations and compute distance from them, which gives you basically a judgment of similarity or discriminability. So discriminability, I already gave you a description of the ABX task, but you can also probe higher levels to extract like similarity judgment, semantic similarity judgment. Okay, it's the same notion. You just compute the distance, and you test it on different tokens. And then, as for the probabilities, you can present it with like a word a known word and ask whether the probability it assigns it to the stimulus is higher in the case of a word like brick as opposed to a known word but possible word in English like blick. Similarly, you can run accessibility judgments like they like versus they likes and see whether the system is able to capture some of that. And so, so basically the ABX, I'm not going to say much except that we sort of, even with quantized and discrete tokens, we have pretty good ABX score. So these are different models like the CPC I described, and then the other two models, Schubert and Wave-2-Vec, as a function of the number of units. And this is here the bit rate. So that represents, I mean, the sort of, the more units you have, of course, the higher the bit rate. And basically, we would like to be as low bit rate as possible, but still with good quality encoding. And this is give you a sort of this trade-off that's going on here. In this graph, there's the language superiority effect, which is like the similar to RL I presented before, except that now it's between English and French. And as you can see in this graph, as you increase the training size of the system going from 50 hours to 200 hours, the size of the superiority effect is increasing. It's actually increasing even more after you do the quantization than before. Okay, so now the results on the lexical spot the word task. So in spot the word, I give you two words, you give me which one is which, one word, one non-word, like Dick and Brick. The chance level is 50%, and here we represent the performance of a system based on different frequency bands of the words. So here are very infrequent words, the words that the system has only seen up to 5 times in the training corpus. And here you have like more than 100 times. And what is typically found in text, so this is like text systems like BERT trained on text transcriptions of the training set. And typically the performance on this spot the word task is pretty high. But there's a frequency effect, so you have better performance with higher frequency words. And in blue, this is the performance of our unsupervised system based on contrastive relative coding with 100 units, followed by BERT. And you can see that it's way above chance. And so that means that our system completely unsupervised has learned something lexical. The other results I wanted to share with you is the acceptability judgments. So to test that, we made a spoken adaptation of the BLIMP dataset. So BLIMP is for benchmark of linguistic minimal pairs that was recently published. And so these minimal pairs are like this. You have like basically linguistic minimal pairs. Many girls insulted themselves versus many girls insulted herself, etc., etc. So there is a bunch of different categories of violations of linguistic rules in the language. And so we synthesized this with a speech synthesizer, and we presented it to our system that has been trained with 1,000 hours of speech. And so there's a big table here, but basically the more green you are, the better. So these are here models trained on text, and the performance is about like 80% correct, which is close to human. I mean, humans are also like around the 90s. They are not 100% correct in this task. So actually, this is the human. The text-based system is slightly lower, and our system is 56% on average, which is pretty close to chance, but sort of, I mean, significantly higher than the 50% chance. And you can see that there are certain categories which gets very well, like the ellipses and the quantifiers, but some others are bad, even like go in the wrong direction. So there's quite a bit of noise there, which means that the system really is not really capturing very well the syntax, but it's not doing chance performance. Okay, so I'm going to skip the similarity results because they are not really, I mean, semantic similarity, I believe, are not different from chance. They really, it's super difficult to extract similarity representations from just phonemes alone. And that's what we basically show. Okay, so overall, we compared all different systems, CPC, Hubert, and Wave2Vec with different number of units. And we see the performance of the ABX error, the lexical spot the word, and the acceptability judgment. So the higher level, the worse the performance. But still, there is the notion that basically, if you have better phonetic units, you also have better performance at the higher levels, which is encouraging. Okay, so in conclusion, the systems learn higher order language structure in a non-supervised fashion from the raw signal with no pre-wired linguistic categories at all. It discovers its own quanta. So we believe that it's important for the system to actually do some use discrete units. But the discrete units that we found are not linguistically identifiable in any way that I could find. So, so can we build a system that can achieve the competence of a 2-year-old using only REST data? Well, I think we have made some progress there. The big change came from unsupervised representation learning algorithm based on prediction, which open up the possibility of learning language from pseudophones. And the learning from pseudophone is effective in the sense that it's better than chance. So our systems sort of pass the test that would be that we could run on the infant about the lexical level, and the syntactic level is significantly better than chance, but pretty close to chance still. And the semantic is as present unclear. So in terms of machine learning, there are many challenges. Of course, what we did was simply take out of the box basically language learning, language models. Like we just took BERT. We didn't do nothing to adapt that to the fact that speech is variable in time, that has some noise, that et cetera, et cetera. So we can expect that like more research in machine learning will actually improve these models and give higher performance to these various tests. There's also the incredible fact, I mean, unexpected. I wasn't expecting very good performance even at the lexical level, given that the units are really smaller than this. No notion of word, just like chunks, I mean, basically discretized audio chunks. From the cognitive science, the challenges are to understand what this means about the role of linguistic categories in infants. Now we have models that can mimic some of the psycholinguistic tests. They can mimic the RL in effect. They can mimic the preference for words versus non-words, yet they have no identifiable linguistic categories. So that, I mean, that should basically open up a discussion that we can take up later. And also these models, to the extent that we believe that they really reflect what infants are doing, are going to give a lot of quantitative predictions, very detailed. So now we can basically give an idea of the lexicon, growth of the lexicon. We can have an idea of the growth of the phonemes contrast. And are we able to test these with our current infant paradigms? That's the question that's open. Okay, so more generally, to really conclude, the sort of approach I have been proposing for years is the reverse engineering approach. It's the idea of putting together machine learning algorithms and psycholinguistics and cognition. And I think I've sort of illustrated that it is interesting for both sides. So from the point of view of AI, it raises interesting core machine learning problems. And eventually it will, when it works, it will enable like more adaptable AI applications because now you don't need any text anymore. And for cognition, it provides quantitative models for developmental science and can give some useful tools for language analysis. One of the thing that we should all be looking at now is to go from these corpora, which are speech, but they are not extremely ecological. So it's not the case that parents are reading books all day to children. So what happens when you go to more ecological data is still an open issue. Okay, so I would like to thank my team. So on the left, there's my academic team at the EHESS. And on the right, there's my team at Facebook, and it has been a fantastic collaboration. Thank you very much.